Imagine standing at the edge of everything. Not the edge of the Earth, not the edge of the galaxy, but the edge of existence itself. The place where time, space, matter, and energy dissolve into nothing. And then ask yourself the most unsettling question of all. What was there before it all began? This question is older than science itself. Ancient cultures wondered about creation, often imagining gods, chaos, or eternal cycles. But today we have physics. And physics tells us a story that begins 13.8 billion years ago with a moment we call the Big Bang. But here's the catch. The Big Bang theory, powerful as it is, doesn't actually explain the true beginning. It describes how the universe evolved after it became hot and dense. What it cannot yet answer is what, if anything, came before. And that's where the mystery deepens. Long before telescopes, humans gazed up at the night sky and asked, where did it all come from? For the Babylonians, the world emerged from a watery chaos. For the Greeks, some imagined an eternal cosmos, never created, never ending. In India, Hindu cosmology spoke of endless cycles of creation and destruction, the cosmic dance of Shiva forever repeating. In Norse myth, a void called Ginnungagap gave birth to fire and ice, colliding to spark life. These were not scientific theories, but they reflected a deep intuition. Beginnings matter. Fast forward to the early 20th century. For centuries, Western science largely followed Aristotle's view. The cosmos was eternal and unchanging. Even when Galileo pointed his telescope at the heavens or Newton described gravity, the deeper question of origins seemed too vast, too abstract. When Albert Einstein first wrote down his equations of general relativity in 1915, they seemed to predict something shocking, that the universe should be either expanding or contracting. But Einstein, like most scientists of his time, believed the universe must be static. So he modified his equations, introducing a cosmological constant to hold the universe still. Later, he would call it his greatest blunder. In the 1920s, a young astronomer named Edwin Hubble used the most powerful telescope on Earth to observe distant galaxies. To his surprise, their light was stretched, redshifted, meaning they were racing away from us. Not only that, the farther they were, the faster they seemed to be moving. This was the first evidence that the universe was expanding. If space is stretching today, then yesterday it was smaller, and the day before that, smaller still. Extrapolate far enough back, and you arrive at a moment when everything, all stars, all galaxies, all energy, was once compressed into a single, unimaginably dense point. The universe, it seemed, had a beginning. The universe had a beginning. At least that's what the evidence seemed to say. But what exactly was that beginning? When people hear Big Bang, they often imagine an explosion, fireworks erupting in the darkness of space, a single spark igniting the void. But this is misleading. The Big Bang wasn't an explosion in space, it was an expansion of space itself. At the earliest moments we can describe, the universe was a seething ocean of energy, hotter and denser than anything we can truly imagine. Not a fireball sitting in empty space, but space itself, stretched tight, packed with radiation and particles, all moving together. And as space expanded, it cooled. From that cooling came structure, first atomic nuclei, then atoms, then galaxies, stars, and planets. Everything we see today is the result of that ancient expansion. How do we know this? There are three main pillars of evidence that support the Big Bang. First, the expansion of the universe. Edwin Hubble's discovery that galaxies are rushing away from us, and the precise law that the farther they are, the faster they go. This is exactly what we'd expect if space itself is stretching. Second, the cosmic microwave background. In 1965, two engineers, Arno Penzias and Robert Wilson, were testing a radio antenna when they noticed a faint hiss like static that they couldn't get rid of. They thought it was pigeon droppings inside the dish. But it turned out to be something far more profound, the afterglow of the early universe. This light, stretched into microwaves by billions of years of expansion, is a snapshot of the cosmos when it was just 380,000 years old, a baby picture of the universe. And it matches the predictions of the Big Bang with stunning accuracy. Third, the abundance of light elements. In the first minutes after the Big Bang, The universe was hot enough for nuclear reactions. In those fleeting instants, hydrogen fused into helium along with traces of lithium. The exact ratios we see today, about 75% hydrogen, 25% helium, are precisely what Big Bang nucleosynthesis predicts. Together, these lines of evidence form one of the strongest scientific theories ever constructed. But even with this evidence, misconceptions persist. The Big Bang does not say the universe came from nothing. It does not describe the origin of space and time themselves. It does not take us all the way back to the very beginning. Instead, it describes how the universe evolved from a hot, dense, rapidly expanding state. A state we can trace back confidently to a fraction of a second after the start. But if we try to go further, to T0, the very first instant, our equations stop working. Mathematically, if you rewind the expansion all the way, you reach a singularity, a point of infinite density, where space and time themselves collapse. But infinities in physics usually mean something else. Not that reality becomes infinite, but that our current theories are incomplete. Just as Newton's laws fail at the speed of light, our current picture of the cosmos fails at the very beginning. Einstein's general relativity describes the geometry of space and time beautifully. Quantum mechanics describes the microscopic world with astonishing precision. But at the Big Bang, we need both, and the two don't yet mesh into a single, unified theory. The result? A veil. A boundary beyond which our knowledge cannot yet penetrate. This is where speculation begins. Physicists ask, if the Big Bang wasn't the true beginning, then what was it? Could the universe have existed before? Could there have been something else, some deeper structure of reality from which our cosmos emerged? Some propose that the Big Bang was not the first event, but just one chapter in a longer story. Others suggest that time itself may have no meaning before this point. To move forward, we must examine the boldest theories of modern cosmology. Ideas that attempt to peek behind the curtain and glimpse what, if anything, came before the Big Bang. So if the Big Bang isn't the ultimate beginning, what could it have been? Physicists have proposed several bold possibilities, none proven, all speculative, but each an attempt to extend our reach into the unknown. Let's explore them, one by one. One, eternal inflation. In the 1980s, cosmologists developed the theory of cosmic inflation to explain some puzzles in the Big Bang model. The early universe appears remarkably uniform, the same temperature in all directions, despite regions being too far apart to have exchanged light or heat. Why? Inflation proposes that, in the tiniest fraction of a second after the Big Bang, the universe expanded faster than light itself. Not matter through space, but space itself stretching at extraordinary speed. This rapid expansion would smooth out irregularities, explaining the cosmic microwave background's uniformity. But here's the twist. Inflation may never completely stop. In some regions, it ends, giving rise to bubble universes like ours. In others, it continues, endlessly spawning new universes. This idea is called eternal inflation. If true, our Big Bang was just one bubble among countless others, a local beginning, not the ultimate one. The multiverse in this picture is infinite and eternal. But eternal inflation raises its own questions. If universes are constantly being born, what governs the process? And is it even possible to test scientifically, or is it forever beyond our reach? Number 2, the cyclic or bouncing universe. Another idea challenges the notion of a one-time beginning altogether. What if the Big Bang was not the first bang, but merely the latest in a series? Some models propose that the universe goes through endless cycles of expansion and contraction. In this view, the Big Bang wasn't creation ex nihilo, but a bounce, the universe rebounding from a prior collapse. Einstein himself once considered such a possibility, but dismissed it. Later in the 2000s, theorists inspired by string theory revived the idea, imagining a brain collision in higher dimensions. Two parallel universes could collide, triggering a Big Bang, separating again and eventually repeating the dance. This cyclical picture is elegant, but it comes with challenges. Each bounce must somehow erase the entropy, the disorder, built up in previous cycles, or else the universe would accumulate chaos until no structure could form. Still, it's a tantalizing vision, a cosmos without a true beginning or end, pulsing eternally like a heartbeat. Number 3. Quantum beginnings. At the deepest scales, the rules of quantum mechanics dominate, and when we apply them to the universe itself, strange possibilities arise. Physicist Stephen Hawking, along with James Hartley, proposed the no-boundary hypothesis. According to this idea, the universe didn't emerge from a singularity at all. Instead, time itself may have a different nature near the origin, more like space than time. Imagine traveling toward the North Pole. As you move northward, the lines of longitude converge until eventually there is no further north. The pole is not a boundary, just a smooth point where the directions end. Similarly, Hawking suggested time could round off near the beginning. The universe would then be finite but unbounded, without a sharp moment of creation. Asking what came before would be as meaningless as asking what's north of the North Pole. Other quantum cosmology models propose that the universe could spontaneously arise from a quantum fluctuation, a sort of nothing, though not truly nothing in the everyday sense, but rather a quantum vacuum, rich with potential. To some, this seems unsatisfying. It replaces one mystery with another, but to others, it offers a glimpse of how physics might replace metaphysics at the very boundary of existence. Number 4. Conformal Cyclic Cosmology. Nobel laureate Roger Penrose has proposed yet another vision, Conformal Cyclic Cosmology. In this model, the remote future of our universe, billions upon billions of years from now, when all matter has decayed and only radiation remains, is mathematically indistinguishable from the ultra-hot dense state of the Big Bang. Penrose suggests that the end of one universe naturally becomes the beginning of another. In his words, the end of time is the beginning of time. He has even claimed tentative evidence, patterns in the cosmic microwave background that might reflect events from a previous aeon. These claims are controversial, but the idea remains one of the most imaginative attempts to link cosmology across the ages. Number 5. String theory pre-Big Bang. Finally, in the vast mathematical landscape of string theory, some physicists have proposed pre-Big Bang scenarios. In these models, our universe may have emerged from a collision or interaction of higher dimensional objects, brains short for membranes. Such collisions could release enormous energy, igniting a new universe. Others suggest the universe might oscillate in strange ways through extra dimensions, with each cycle creating something like a Big Bang. Though highly speculative, these ideas attempt to use the mathematics of string theory to answer the oldest of questions: what came before? Each of these theories, eternal inflation, bouncing cosmologies, quantum beginnings, cyclic aeons, string theory scenarios, offers a different answer, and yet none are proven. The evidence we have still points only as far back as that primordial glow, the cosmic microwave background. Beyond it, we are left with conjecture, imagination, and equations reaching for truths they cannot yet grasp. The deeper question remains: is before the Big Bang even a meaningful phrase? Or is the very concept of before a trick of human intuition, something reality itself may not recognize? Time. It's so familiar, so constant, that we rarely stop to question it. We measure our lives in minutes, days, years. We feel its flow. We assume it always was, and always will be. But when we ask what happened before the Big Bang, we're forced to confront a possibility few find comfortable. Perhaps time itself had a beginning. Einstein's theory of relativity revealed something radical. Time is not a universal tick-tock, separate from the cosmos. It is bound together with space into a single entity, space-time. Mass bends space-time, motion stretches it. The faster you go, the slower time flows. Near a black hole, clocks tick differently than they do on Earth. Time is not absolute. It is woven into the structure of the universe. So when we trace the universe back to the Big Bang, we are not only rewinding matter and energy, we are rewinding time itself. At the Big Bang, space and time both seem to emerge together, which means asking what happened before may be like asking, what's north of the North Pole? One interpretation of relativity is the so-called block universe. In this view, past, present, and future all exist simultaneously, like pages in a book. We experience them sequentially, but the whole story already exists. If this is true, then the Big Bang is not a beginning in time. It is simply one slice of a four-dimensional block. There is no before or after in an absolute sense, only a timeless structure with us traveling through it. But this view raises philosophical dilemmas. If the block universe is real, then the flow of time, our sense of passing moments, is an illusion. And the notion of before the Big Bang is meaningless, because the Big Bang is just part of the eternal block. Yet relativity isn't the whole story. At quantum scales, time behaves even more strangely. In some approaches to quantum gravity, time doesn't appear as a fundamental quantity. Instead, it may be an emergent phenomenon, something that arises from deeper, timeless laws of physics. Imagine a river. From a distance, it seems like a smooth flow, but zoom in, and you find molecules of water, each moving chaotically. The flow is not fundamental, it's a pattern we see at large scales. Some physicists suggest time may be similar. At the deepest level, there may be no before and after, only a vast, timeless reality from which our sense of time emerges like the flow of a river. If that's true, then the Big Bang might not be a beginning at all, but a transition in a timeless landscape. So when we ask what came before the Big Bang, we might be making a category error. We are imposing human intuition, the way we experience time, on a universe that may not work that way. To a fish, water seems fundamental. To us, it's just a medium, part of a larger world. Perhaps time is our water, a medium we swim in, but not the ultimate reality. The unsettling truth is this: it may be that there is no before. The Big Bang may represent not the start of the universe, but the start of time itself. And yet, even if time itself began with the Big Bang, the human mind refuses to rest. We want to ask, why did it begin? Why this beginning and not another? Here, science begins to blur into philosophy and perhaps into something deeper. At some point, physics reaches its limits. Equations break down. Experiments cannot probe further. And yet our curiosity doesn't stop. We still ask, why? What came before the Big Bang may not be just a scientific question. It is also a philosophical one, perhaps even a metaphysical one. Science is powerful because it builds on evidence. We construct models, test them, and discard what doesn't work. But when we ask about before the beginning, evidence grows thin. The cosmic microwave background is our oldest light, our deepest window into the past. Beyond it, direct observation becomes nearly impossible. Gravity waves might one day carry whispers from earlier times, but for now, the data ends there. So science must rely on theory, on extrapolation, on speculation. But speculation without testability borders on philosophy. This does not mean it's useless. Philosophy has always been the foundation beneath science. But it does mean we should tread carefully and distinguish what we know from what we imagine. Philosophers have long asked, must everything have a reason? Must there be a cause for every effect? If so, then the universe must have a cause too. But if not, perhaps the universe simply is. Leibniz in the 18th century argued that nothing happens without a reason. To him, the existence of the universe required an explanation beyond itself, what he called a necessary being. In contrast, some modern scientists argue that the universe may need no cause at all. Quantum physics, after all, allows particles to appear spontaneously from a vacuum. Perhaps the universe is just a grand version of this, a self-contained event, needing no before. There is another puzzle. The universe seems oddly well suited for life. The strengths of forces, the masses of particles, the expansion rate of the cosmos all fall into narrow ranges. A little different, and stars wouldn't form, or chemistry wouldn't work, or life would never emerge. Some see this as evidence of design or purpose. Others point to the multiverse. If countless universes exist, each with different laws, then it's no surprise that we find ourselves in one where life is possible. This reasoning is called the anthropic principle. It doesn't explain why the laws are what they are, but it does explain why we shouldn't be surprised to observe them. Here we encounter a profound possibility. Maybe the question, what came before the Big Bang, cannot be answered, not because the answer is hidden, but because the question itself is flawed. It assumes time is fundamental. It assumes causality applies outside the universe. It assumes the human mind, evolved for survival on Earth, can grasp the deepest structure of reality. But perhaps these assumptions fail at the edge of existence. As Wittgenstein once wrote, "Whereof one cannot speak, thereof one must remain silent." And yet, silence is not satisfying. Humans are not built to stop asking. Even if the question cannot be answered, it remains valuable, because it forces us to confront our limits, because it inspires new physics, new mathematics, new ways of seeing, because it reminds us that mystery is not a defect in knowledge, but the fuel of discovery. The Big Bang is not the end of our curiosity, it is the doorway to deeper questions, questions that blur the boundary between science and philosophy, between knowledge and wonder. Perhaps we will never know what came before the Big Bang, but in seeking the answer, we glimpse something larger, the fragility of our understanding, the vastness of the unknown, and the miracle that we, small creatures on a small planet, can even ask. The mystery of what came before the Big Bang feels eternal, untouchable, and yet science has a way of turning impossibilities into questions, and questions into data. What today feels beyond reach may tomorrow be written in the sky itself. So what might the future hold? How could we test the boldest theories of cosmic beginnings? Our deepest window into the past is the cosmic microwave background, the faint afterglow of the early universe. But what if there are signals even older? Some theories predict primordial gravitational waves, ripples in space-time itself, generated during cosmic inflation, long before atoms or light. Unlike light, gravitational waves can pass through matter almost unimpeded. If detected, they could carry information from the very first instance of the universe, perhaps even from before inflation itself. Experiments like LIGO and Virgo have already detected gravitational waves from black holes and neutron stars. The next generation, space-based detectors like LISA, may one day hear the faint murmurs of the universe's birth. If we could read them, they might reveal whether inflation happened, whether the Big Bang was a bounce, or whether something else entirely unfolded. Other theories predict that if our universe is just one bubble in a multiverse, then collisions between universes could leave marks, scars, in the cosmic microwave background. Physicists have searched for circular patterns, temperature anomalies, or unusual alignments that might hint at such collisions. So far, the evidence is uncertain, but the search continues, and new, higher-resolution surveys may sharpen our view. Imagine one day discovering that our universe once brushed against another, leaving behind a cosmic fingerprint. It would change everything. If the universe could emerge from a quantum vacuum, then understanding that vacuum is crucial. At particle accelerators like CERN, scientists probe the quantum fields that underlie reality. Each discovery, the Higgs boson for example, refines our understanding of what nothing really is. But perhaps new physics beyond the standard model holds the key. Supersymmetry, extra dimensions, or other hidden structures might one day reveal whether nothing is unstable, capable of birthing entire universes. Another path may come not from looking outward, but from rethinking time itself. Why does time flow forward? Why do we remember the past but not the future? If we could solve the riddle of time's arrow, we might learn whether time began at the Big Bang, or whether it extends further back, perhaps even in two directions. Some theories suggest a mirror universe extending backwards in time, a cosmos where entropy decreases as ours increases. In such a picture, the Big Bang would be less a beginning and more a point of symmetry. It is tempting to imagine that someday technology will answer everything, that a telescope will peer through the Big Bang, or a particle collider will recreate it in miniature. But there may be limits. Some horizons may be absolute, yet even then, imagination remains. And imagination drives questions, and questions drive experiments, and experiments drive discovery. As long as we keep asking, the boundary between mystery and knowledge will continue to shift. The truth is, we don't yet know what futures await cosmology. Maybe we will one day map the very birth of time. Maybe we will detect evidence of universes beyond our own. Or maybe we will discover that the question itself, what came before the Big Bang, has no scientific answer at all. But the pursuit itself is valuable, because every time we reach for the beginning, we learn something new about the universe and about ourselves. So, what came before the Big Bang? We've traced the journey from ancient myths to modern physics. We've seen the strength of the Big Bang model and the veil it cannot pierce. We've explored bold theories, eternal inflation, bouncing universes, quantum beginnings, cyclic aeons. And we've wrestled with the possibility that the very question itself may be flawed, because time may have begun with the Big Bang. Where does that leave us? It leaves us here in the tension between what we know, what we guess, and what may forever lie beyond our reach. The great achievement of science is not that it has all the answers, but that it knows where the answers end. Physicists don't claim certainty about what came before. They map the edge of knowledge with equations, with telescopes, with experiments. And at the boundary, they admit we don't yet know. This humility is not weakness, it is strength, because it keeps the door open to discovery. There's a strange beauty in the fact that the universe hides its origins. It reminds us that mystery is not something to fear, but to celebrate. Because mystery means there is more to learn, more to imagine, more to explore. The question of before the Big Bang may never have a final answer. But in asking it, we stretch the human mind to its limits. We confront infinity. We touch the edges of existence. And in that confrontation, we grow. No matter which theory, if any, proves true, the story belongs to all of us. Every culture once told myths of creation. Today, our myth is scientific, but no less awe-inspiring. It is written in the language of mathematics, confirmed by experiments, but still filled with wonder. It is the story of a universe that gave rise to galaxies, stars, planets, and, against all odds, creatures like us. Creatures capable of asking about beginnings. Maybe we will never know what came before the Big Bang, but perhaps the act of asking is enough, because in the question we find meaning, in the search we find wonder, and in the mystery we find ourselves. Step outside on a clear night. Look up. The stars you see are suns burning billions of miles away. Beyond them are galaxies, hundreds of billions of them, and beyond those perhaps other universes, unreachable, unimaginable. All of it stretching out from a moment we call the Big Bang. And here you are, a fragile creature, a collection of atoms, wondering about it all. On the scale of the cosmos, we are tiny. Our lives are brief. Our planet is a pale speck orbiting an ordinary star in a minor arm of one galaxy. And yet, we ask questions that stretch across all time and space, questions about beginnings, about endings, about what lies beyond. Questions the universe itself may never answer. This is our paradox, cosmically insignificant, yet uniquely able to wonder. Some might say, why bother? If the question has no answer, why ask? But to ask is human. It is what makes us more than survival machines. It is what built science, art, philosophy. It is what carried us from caves to cities, from Earth to the moon. What came before the Big Bang is not just a scientific question. It is a mirror we hold up to ourselves, a way of asking, who are we in this vast universe? Perhaps there is no before. Perhaps time began with the Big Bang. Or perhaps there was a multiverse, a bounce, an endless cycle. Or perhaps the truth is something we cannot yet imagine, something no equation, no telescope, no mind can grasp. But maybe that's the point. The universe doesn't owe us answers, and yet it gives us something better, the ability to seek them. The question of what came before the Big Bang may remain forever unanswered. But as long as we keep asking, we remain explorers. Explorers not of land or sea, but of existence itself. And in the end, maybe that is enough.